Hello, this is the Motion Capture Lab Setup Group. I'm Paul Araby,
I'm Patrick Bishop.
And I'm Gabriel Schmidt.
and this is what we've been working on all semester. So, uh, access to proper facilities and equipment is really important for our students to be able to pursue studies that really interest them, especially in classes like 401. So, our idea was to set up a motion capture laboratory that hasn't been used in a few years with the hope of creating something that students in the future may be able to use to further their own studies and say motion capture if that's something they're interested in. Just give them the option. As kind of stated, the objective is to set up this motion capture laboratory so it can be used by other people and to capture multiple trials of human gait data to help determine the precision of the laboratory setup as just a measure of how useful the actual lab is. Nothing is particularly new about this. We're not coming up with anything new. We're not designing this motion capture system ourselves. Everything is readily available already. It's just this would be creating a new resource for this campus for students to be able to use. That's the whole thing behind it. The significance is uh, it can help students with their studies. It can create more interesting options for everyone to get into, and that's all there is to it, really. So here's the method. Our experimental plan, it was a couple stages involved before we could actually get to our test to determine the precision of the system. So we had to actually set up the lab equipment. We had to get the lab equipment in the first place. We had to consult Dr. Hoover on this since most of the lab equipment that we were getting was in storage and we didn't have access to this. Once we had the equipment, we researched the hardware and the software we were going to be using just so we could get familiarized with them, learn what we needed to do, how everything was going to work. We then went on to find a sufficient capture area space somewhere where we could set everything up and run our experiment. We ended up settling in the mechanical engineering laboratory where 401, 301, and 201 are held. We were able to get a little corner off to the side where we were able to set up our experiment. Next, we had to go through and figure out how to calibrate the system because without the calibration, everything we get out of the system would just be useless. So we had to understand how this procedure worked, what we could do to reduce image error involved, so how we could get better and better results. And then we also had to mark boundaries of the capture area where the cameras stopped overlapping all the way and our actual data would suffer if we went outside of that bounds. From there, we went on to our precision test, our actual experiment, which was all about producing or determining system reproducibility by running multiple trials from different subjects, the subjects being us, and the trials being 3 for each of us, to determine just how repeatable the results we would get from each trial are, how well they would match each other. And we took that to be kind of an indicator of how useful this would be. Could you actually use this system to do a study and get results that you'd actually be able to make some sort of conclusion from and that would actually mean something? This is the laboratory setup. There's some cameras over in the back there. There's the volume set origin plate is in the middle. And that's pretty much it. This is also part of the setup. This is tape marks for the bounds. The red X or plus mark in the center, that's the volume set origin place. That would be the origin of the entire capture area. And the black marks show how far we can get away from that before the cameras start to not overlap anymore exactly. These are some pictures just showing us filling in the calibrations. We ran multiple tests trying to figure out better ways of getting of reducing image error. So we tried changing how fast we swung the calibration wand. We changed how many reference frames we would use. All sorts of different parameter changing that we tried, and we found that the results were kind of inconclusive. But we did end up being capable of getting really good errors somewhere around 0.3 to 0.25 the majority of the time. And then the picture all the way to the left that's different from the rest here is just a picture of the Vicon setup itself with all the cameras set up. The volume center has been set, and it just shows the entire lab setup, just minus everything except the cameras, pretty much. So this is our test procedure. It's very long, pretty tedious, but basically would involve turning on the computer, opening the application software, configuring the software for our calibration test. We chose to go with 2,000 reference frames, but suggested between 2,000 and 3,000. We didn't see too much of a difference, so we just went with 2,000 since it was the fastest. We ran our calibration. We would wave our wand around, or we waved the wand around briskly just to get the. It just tended to capture the actual wand better if it was moved kind of quickly. And we made sure to keep the wand in the capture area so that each camera saw its movements and it wasn't just going off of any camera's view. Once the calibration was finished, we checked the error. If the error results weren't what we desired, we would restart the calibration, or depending on how severe the error was, we would refine the calibration, see if that helped at all. Sometimes we wouldn't have to recalibrate every camera. We would just select certain cameras and recalibrate them or refine them. With those error values, we then would move on to setting the volume origin, and that would complete the calibration. From there, we moved on to the subject capture and processing. We would set up a data management trial inside Vicon Nexus, which was the application we were using. We record the subject moving. In this case, it would just be walking in a single straight line, directly starting at the volume center origin, going to the outer bound, and then coming to the opposite outer bound and coming back to the center. After the trial would be done and recorded, we would move on to the pipeline selector inside the software, where we would do the processing so that the actual motion would be recorded, all the calculations would be registered, and then we would export data after naming all the markers so that we could keep the points on our body so we could differentiate them. We would export it through the option export data to ASCII file, which would create a comma-separated value file. In this case, we used the header and trajectory options that open up them there. This would give us X, Y, and Z position data in relation to the origin for each point that we used. Our equipment, this is just a short list. We used 4 Vicon infrared motion cameras. We did have more, but we decided to work with 4 since it just fit the lab space the best. And also we figured that if we were able to get good results with only 4 cameras, it kind of showed that this system, even at bare minimum, is really powerful and worth spending time with. We use the Vicon motion software for capture. So Vicon Nexus, that's what it was. Calibration equipment, including the calibration wand, the volume origin triangular plate. Our computer was Windows XP desktop PC with a ViewSonic computer monitor. And then we also had Vicon sensor data hardware array, which was 3 units stacked on top of each other that would interface with the cameras and process data to send to the computer and then into Vicon Nexus. Our safety risk assessment essentially stated that this is a very low risk experiment. Most of our hazards were heavy objects that may move if not properly secured. This took the form of cameras mostly, just because if they weren't very well centered or secured, they would potentially fall and hurt someone or themselves. This is taken care of by just making sure to pay attention to how they were prepared and keeping them where they needed to be. Contact with electronic components, essentially just making sure we weren't sticking forks in outlets. That's pretty much the extent there. tripping hazards. There was a big metal grate in the middle of the capture area, but we were able to set up our motion so that when we were walking, we were far away from the grate and it wasn't going to be an issue. We also had the issue of moving objects, which basically meant that when we swing around the calibration wand, there is a chance that we could hit someone or ourselves. So to kind of not have that happen, we kept people outside of the capture area whenever they didn't need to be in there, especially during a calibration. And we also just tried to stay to our own respective areas. If someone was working with the computer, stay with the computer. If someone's doing the calibration, stay with the calibration, and don't go near them when they're swinging the calibration wand, kind of deal. Very common sense stuff, was not very super involved or anything like that. Although if there was any serious injury or any problems, our lab setup was in the ME lab, so we had access to emergency safety equipment, and both campus-based and local medical professionals were available if anything happened. So from our precision test, we were able to get some results. This was the primary data. This is the exported CSV files compiled together. Each one of those long kind of looks like a bar, kind of like a barcode. Each one of them was an exported file that has been since compiled. There's a lot of data here. These trials went on for around 15 to 30 seconds, taking data maybe every 2 seconds or less. Each point that we used, of which there were 6 for each trial, has X, Y, and Z coordinates. And we ran 3 trials for 3 subjects. So a lot of data. Really hard to show off here. We experimented with some figures, but it was completely unreadable. So we really needed a better way of kind of comparing everything, which led us to our analysis. We decided to go with creating an average segment length, overall trials and times. Essentially, we would take for a given time an average from each trial and then average all of those numbers together. So for each trial for each time, there would be an average segment length over the trials, and then that was averaged to get the final average segment length for every trial and time. These segments were the lower leg, upper leg, lower right or lower left leg, upper left leg, lower right leg, and upper right leg, corresponding to the connection between the ankle and the knee and the hip. So we then also created an average range overall trials and times. This would be taking from the 3 trials at a specific time, the maximum segment length from those trials minus the minimum. So just the largest minus the smallest, creating a range. And then this was done for every time that was recorded, and then all those numbers were averaged to get an average range. As a kind of a final idea for how precise or how much these numbers would vary amongst themselves, we had an average range as a percentage of average segment length, taking the average range and dividing it by the average segment length. We also called this percent difference length. For the most part, this was below 3%, which we thought was fantastic. And even more so that the majority of these percent differences were around 1%, which, again, fantastic. We're talking, 1/100th of a millimeter different, or 1 millimeter differences, which was great. So, in conclusion here, we got some key takeaways. We're able to get reproducible low image error calibration. We'll be able to pass on our techniques for doing this to future students if they want to be able to do or do any experiments with this setup. We found that the system we believe to be reasonably precise based off our results. The percent differences were very low, most of them being around 1%, with the ones that were above possible sources of error being that it was the first subject that went, so we were still kind of getting into the hang of everything. Um, then we also were able to take away the fact that we gained a lot of knowledge in the setup of how this lab was supposed to be run. So we will be able to pass on this information and documentation, so people who come after us would be able to set up this lab, produce their own experiments, and just do what we set out to do. Creating a resource for the people who come after us. Some possible next steps here, if we want to make the experience better or improve what we have been doing here, would be improving the experiment. So maybe we can test for accuracy too. We set up a rig that basically will have something move in a predictable manner that we know where exactly it would be through measuring its position physically with like a ruler. We know exactly where it's supposed to be, and then compare that to the data that Vicon Nexus would spit out at us. We can also test for more error reduction methods during calibration. This could involve changing other parameters, like say wand speed. Can find a new and better lab space so that we would be able to increase the number of cameras we use, hopefully creating more precise data just through the more cameras being used, more points and more perspectives the data could be taken from, just making all around the calibration and actual motion capture way easier, since more cameras are able to pick up on the same points and cross-reference themselves. And with that, we'd like to acknowledge a few people here. We'd like a special thanks to Dr. Carl Hoover for being our project advisor and for his help in organizing the location for our motion capture experiment and experiment capture area. Without him, we wouldn't have been able to get any of the equipment. It would have been locked in storage far from our grasp. We would also like to thank Dr. Kwadwo Appiah-Kubi, I'm really sorry if I mispronounced that, for his own motion capture equipment and providing access to Clarkson downtown Potsdam campus. He presented us with a wonderful opportunity to come get more equipment. Unfortunately, we kind of ran out of time on being able to use some of it, like force plates, but that is also a further step that we could look into in the future. Lastly, we would like to thank the members of the Clarkson MEA 401 dartboard group. They were also working with the same system, trying to set everything up, kind of getting the hang of it. So we were able to work together a bit on finding system documentation and on setting up the actual motion capture equipment in the lab space we had. Here's our contributions, Patrick, me, Gabriel, and thank you so much for your time.